Okay, let's kick it off. Hello, everyone. My name is Josh. I'm one of the co-organizers here at Cloud Native at Scale. We're a meetup community for those of you who don't know. Sometimes we have some people that come from Eventbrite who may not be a part of the community, but I invite you to join us. The community is Cloud Native at Scale. We're based in San Francisco. Obviously, right now we're doing online events because we can't meet up in person, but hopefully we can do that later this year. For those of you who don't know, we're focused on bringing together some of the best cloud native architects around, senior architects at some of the largest technology companies and companies out there. Today we have Marco from Adobe. First of all, I just want to thank you, Marco. Thank you so much for being here and spending time with us. These events would not be anything without our speakers, so we really appreciate that. I'm going to quickly turn it over here to Daniel. Daniel Cohen is senior, or is a director of customer success at Styra. And Daniel, why don't you go ahead and introduce yourself and tell us a little bit about what's going on in your world?
Sure, thanks, Josh. So you got the title part right. My background is largely in financial softwares and building trading systems for big investment banks. Done that in a couple big cities around the world. And then I spent some time around selling various technologies back to those banks. That'd be the easy way to put it. But today I'm director of customer success at Styra, and you may know us as the creators and the maintainers of the Open Policy Agent. And Josh is being generous enough to let me, mention that we recently graduated from, however you phrase it, the Cloud Native Computing Foundation. That's a very big deal for us. It's a very big deal for any project. For Open Policy Agent, it means we've gone beyond simply adoption by a community, and we're really, we're deeply used and depended on by large enterprises. That's part of the graduation process. You have to go through various stages, the sandbox, the incubating, and so forth, before you can even get to this point. But at this point, we've had, endorsement by large companies. We've had endorsement by multiple committers, multiple members of the board at CNCF. It's a very important moment for us. We've also been really excited to get all of the congratulations emails from around the world. It's been incredibly, it's been a fun time for us. So thank you, Josh, for letting me take the time on that. If you don't know Open Policy Agent, it's a general purpose policy engine and decision engine. Lets you basically make decisions about structured data and spit back out different structured data. We're often used as a Kubernetes admission controller. We're used for Envoy use cases for ingress, egress, and app permissions. There's a lot of great use cases out there, and it's been an interesting journey. I think that's about all I need to say about that. So
Daniel, real quick, what are you hiring for right now? So I know you guys are exploding right now and you're doing a ton of hiring, but just in general, we have a lot of engineers on the line. Is there anything in particular you're hiring for?
We are hiring for all flavors of engineer, whether front or back end. We're hiring pre-sales, post-sales, sales. I mean, goodness. I think there are a lot of positions. There are a few on the website and many more that are not tendered to the website as well. So you name it, man. A lot of good stuff happening. Yeah. Yeah. If you're curious, drop me an email. Happy to talk about it. But yeah, it's an exciting time. So shall I introduce the good doctor then?
Yeah, go for it.
All right. Yeah, I won't take very long to do this, but Marco, self-stated, has been around the block. He's done the startup thing. He's done the big company thing at places like Apple, at places like Adobe right now. I believe you had a stint at Mesosphere as well. I know a few of those folks over in Europe. No problem. But presently in your role at Adobe, you've been doing some interesting work, including some OPA work, which I'm very excited to see more of course. And, and today you have a topic that makes a lot of sense to me. So I spent time with DataStax at the Cassandra project, spent time at AppDynamics. This is very much an intersection of those worlds, very much distributed, but very much monitoring. So I'm curious to see what you have to say about this, and so I'll turn it over to you.
Thank you so much, Daniel, and congratulations to you and the Styra team. As I said, I've been playing with OPA. Actually, just last night I was coding away at my Spring integration with OPA in JWT, so that was good fun. Congrats, guys. Well done. So thanks for the introduction, and thank you, Josh, for having me. Really a pleasure to be here. As Daniel mentioned, I'm now currently at Adobe. I've been, at various other places. I want to be very clear, and this is kind of I need to do this. It's a disclaimer. This is my stuff. You can read the legalese, but the bottom line is that if you like the stuff and you think it's smart, then we are hiring as well at Adobe. So reach out, and we always like smart guys. If you don't like and you think it's dumb, then it's all my fault. don't blame Adobe for it. And also important, jokes aside, this is not production code. This is stuff that I've done for my own education and my own entertainment. From time to time, I grab some transactions or whole technical papers from research and academia, and I implement it. In this case, I did it in C++. Because I can mostly, and because it helps me learn more about distributed systems. Here's a bit of the track of what we'll be talking about today, a bit of the motivation. Why do you want to use something which is called gossip protocol? Typical use cases, an implementation of a gossip protocol. Then you mentioned Cassandra. Cassandra is probably the most famous adopter of a gossip protocol across nodes. I'll talk about that briefly. I'll give a brief introduction about protocol buffers. Hopefully everybody has heard, at least heard of them, knows about them, but I think they're a great technology. It's interesting, I talked to a large number of startups also in my role here at Adobe because we're looking for new technologies. And I'm aware of at least two that are really pushing regard on protocol buffs, which are technologies about 10 years old, but still very valid. Then we'll do the demo. Nerve-wracking, hopefully it should work. It did work 5 minutes ago, so there are good chances that it will not work while I'm doing this live, but we'll see. And then some Q&A at the end. All right.
Should we take a minute to mention the Q&A bit at the bottom right of your screen? So if you do have a question for the doctor, if you put it in there, we'll be happy to relay those and mention them as they come up. But yeah, please do that. Sorry to interrupt. Please continue.
Not at all. Thanks for that. That was useful. All right. So what's the motivation? Of course, hopefully nobody needs to know why we want to have fault detectors, why we need to figure out which nodes are up and which ones are down. I was for a number of years at Google. When you have about 100,000 to 500,000 servers, even if your failure rate is, you're in the mythical 4 nines, 99.99%. If you do the maths at any given time, you have a few thousand servers that are down. And that's not even the worst part of it. The worst part of it is those servers that aren't quite down, just slow to respond. Those really are the ones that cause trouble. And you need to have a means by which you can identify them, do something about them, at the very least, stop using them and take them out of your rotation. And if you have a load balancer or your replication node or ring or whatever. The typical way of doing that, certainly the way that if you see in the slide in the right corner, Kubernetes does that, is via heartbeats. And so every node will send every so many seconds, will send a heartbeat. And by doing that, or there is a controller. That's two ways essentially. It's either push or pull, or you have a controller node that tries to hit a particular endpoint, the health endpoint, and provided that it receives a response within a given timeout, we'll assume that the server is ready and responding and healthy. The problem with that model, and particularly when all the nodes need to know about each other, is that it doesn't scale terribly well. If every node in a large cluster needs to know about the health of every other node, you do the maths, that's an O square, an ODN square problem, and it grows quadratically with the size of the cluster. It also causes trouble because you may have situations where, due to network traffic, your heartbeat fails to respond within the timeout, The server may be perfectly healthy. It's the network in between that isn't quite that healthy. But you may incorrectly report that server as unhealthy. Take out of a replication node, circle, or whatever, and that's not a good situation to be in. I have a couple of examples here. On the left, I'm using Zookeeper. That was the traditional, probably the best distributed system that came out of Yahoo back in the day. This uses an architecture where you have essentially a master node or a controller node. There's an election. Zookeeper, I think, was the first famous system that you were using Paxos to be resilient to essentially to network partition. It's an eventually consistent system. It means that eventually all the servers, all the nodes will have the same state, but there may be intervals of time during which they may be inconsistent. And the controller node, which is elected, the leader node is elected, takes care of that and keeping connectivity across all the servers. Another example, as I mentioned earlier, is in Kubernetes, where you have essentially the controller node that will keep tabs on the overall health of the various containers or pods in the cluster. The state there is kept in etcd, which is also a very well-known evolution of Zookeeper, and that's where the state is kept. Again, as I mentioned, in Kubernetes, you have the controller node that typically, as you saw in this diagram, is replicated. But there's only one controller node active at any given time, which keeps the state of the whole cluster. Every node, every single node, every pod has no idea about other pods. It doesn't know whether they're up, they're down, what their health is. And finally, at the bottom, as I mentioned, Cassandra instead uses a gossip protocol. In fact, uses something very similar to what I'm going to present today. It's pretty much the same principles. Every node, even though they're represented on a ring, I don't know why, by the way, incidentally, just so you know, there's no good architecture diagram in the Apache documentation of Cassandra. I had to steal it from somewhere else. That particular diagram. The link at the bottom is where it describes specifically the gossip protocol that's used across the nodes. The problem that Cassandra is trying to resolve is that every node can act as the coordinator node for every given request. And then it needs to replicate, if it's a write request, it needs to replicate the write to a number of other nodes in the ring based on the quorum. And they will exist in what is essentially is a ring, which is the representation of the consistent hash. But the bottom line is that every node needs to know which nodes are healthy and which ones they can use to replicate. And then it needs to avoid trying to replicate a node that is not responding, because otherwise what happens is that it will have to wait until it times out. It will wait pointlessly, and that may cause a backlog of traffic, and it may slow down the write speed of the overall cluster. So that's why you use a protocol that's a gossip protocol. I promise you this is the only slide with lots of bullet points, lots of words. I was assuming, Josh, that you will distribute this eventually to the attendants. I wanted to have a place where I collect a bunch of points, but this is the only wordy slide. The idea for the so-called swim gossip protocol is that it's scalable and it can be proven. There's a mathematical proof in the paper, which is referenced at the bottom, that essentially you have an exponent, the speed of spread grows exponentially across the cluster. And so that means the complexity is logarithmic with the size of the cluster. Unfortunately, it's an infection style, and it's a bad time to talk about infections. but essentially, it's very much, the reason why, unfortunately, we're in the middle of a pandemic is that infection typically spread geometrically, or even it can be even exponentially. And the reason, if you think about that, in this particular case, every single node talks to k other neighbors. Assume that the number is 2. Then node number 1 talks to 2 nodes, and then those 2 nodes talk each to other 2 nodes, so it's 4, and then it becomes 8, and you can see how this grows exponentially. The idea is that every node will send a ping to a randomly chose node in its set of neighbors. And then depending on whether it receives a response within a given timeout, we assume that the server is healthy. If it doesn't, then it puts in a particular list they call the suspected list. It doesn't assume that it's crashed. It just says, well, something isn't quite right with this node. Let's figure it out. And the modification that the classic gossip protocol, the swim protocol does, is that it tries to go around it. And it uses a so-called forwarder node. In this example, you can see node number 1 tries to talk to node number 3. He doesn't get anything back. And then he goes to node number 4 and says, dude, could you please try and see if you can reach number 3 on my behalf? If node number 4 can successfully communicate with number 3, it will go back to number 1 and says, yeah, this guy is just fine. You can remove it from the suspected list. This allows the system to essentially route around intermittent network failures from in particular routes, overloads in particular section of the clusters, and essentially makes the system more resilient. The other couple of other important aspects which I mentioned here in this slide is that the routing strategy, i.e. how every node picks which other nodes to talk to, can be tailored. It's not dictated by the protocol. So for example, each node could choose to only communicate to the quote unquote closest node, close in a network sense, i.e. in either low latency or low number of network hops. You can completely choose the neighbor at random from the list. In my implementation, that's what I do. I pick an entirely random number K of clusters or neighbors, and I send the report out. Or you can just connect to the last one where you connected from, which got pinged from. And so depending on what you're trying to achieve in your node, you can also do things like, for example, you can use a bastion host to do bridging across 2 subnets. So you can imagine if you have, in this example, say that the nodes 5, 6, and 7 are in a subnet that's not reachable directly from number 1, well, we can use number 2 to get the health. And then when number 2 will send back a report, I'll show that in a second, then number 1 will know about the health of servers, which are not actually, it cannot directly reach. And the other important thing is that nodes come and go. And that's typical behavior. That definitely was true when I was at Google. Of those thousands of servers that were down, they would come back up, same IP, different IP, same host name, so on and so forth. It doesn't really matter. Essentially, there's no any node doesn't keep a state of the nodes that have gone away. He assumes that if they come back, they're just fine and they can continue to use them. Essentially, every node keeps a state machine of every other node in the cluster. They can be in started mode. Then after they receive a ping, they are in so-called alive state. And so long as the ping is okay, they're still alive. If there's a fail, they become suspected. They go into the suspected list. And after a certain timeout, called the grace period, after a while, I cannot hear back from them. I assume that those are gone. So I'll remove them from the suspected list. On the other hand, if after some time a node that I assume that was suspected to be down comes back either directly or indirectly, then I will move it back into the alive state, and I'll keep there so long as the ping is okay. And the only 2 lists that are kept are all the nodes that are healthy and alive, and all the nodes that are suspected, and that will be removed eventually. I really don't care. The nodes that are being started and the nodes that are being terminated are not really of interest to me. All right. Protocol buffers. I don't know how many people are familiar with protobuf. Like, if there are questions, I'm happy to answer them. But essentially, they've been introduced by Google many years ago. Must have been 15, possibly. Definitely, they were definitely there when I joined in 2007. And essentially, they are a language agnostic way of describing both data format in transit, as essentially they are a serialization protocol, as well as services. They're being used also for nowadays for gRPC. This is not being used at all here, but protocol buffer can be used also to describe essentially remote procedures. In this case, this is an example that I'm using here in my implementation. I describe each server by its host name, the port they need to hit, and the IP address. And then for each event, I have a so-called server record that says, okay, I hit this particular server. I don't know if I move the mouse, is it? No, it's visible. Yeah, okay. So this is the server that I reached. This is when I reached it, a timestamp. It is in seconds from epoch. This is classical C++ behavior. And then if the server was reached through that forwarding mechanism that I mentioned, also which server this went through. And then the one optimization that we make in the Swim implementation is that instead of sending just a ping, we actually use the ping also to carry the report. So every time I reach out to a server, I also send a report with all the list of all the servers that I think are alive and all the servers that I think are suspected that have trouble. And it's important to know that very much like in gossiping, when you gossip, it's your interpretation of stuff that you heard about. May not necessarily be the reality. So one of the things that you will see in the code is that we merge each node's current knowledge of the state of the cluster with the incoming report from other servers. The idea is that those may be inconsistent. Both of them may be, at the moment, not entirely correct view of the cluster, but it will eventually, over time, they will converge to the true state of the cluster. One word about the so-called envelope pattern. Probably everybody's familiar with this. It's at least 10 years old. I found it in the book by Gregor Hope, The Enterprise Integration Patterns. That's interesting. But essentially, the idea is that you have an external format, the envelope, which is somewhat agnostic or polymorphic with respect to its contents, and it's carried over an undifferentiated channel. You can imagine, probably guys, you're familiar with Kafka. You can imagine you have a single topic that you're using, but you want to send different types of messages. The consumer needs to know to deserialize correctly and interpret correctly the message, needs to know what type of message it is. And there can be any number of reasons you want to do that. Maybe you don't want to use several topics. You may not necessarily know what consumers are consuming. There are several use cases for this. In this case, in this example, I'm using so-called proto v2 syntax. And so I carry an enum, and inside the enum will say, okay, I'm sending you just an update, or actually this message contains a full report. So you will have this object, which is optional, will be present there. Or it's a request. This means that I want you to do a forwarding to another server, in which case here there will be destination. This is the server I want you to reach on my behalf. And if you use Proto3 syntax, which I haven't implemented yet, there's actually a much better way to do that, which is using the any.proto model, if you will, and that allows you essentially to serialize any type of payload inside an envelope. And so this could be a different way to implement that. I've in my blog there's a description, a much more detailed description. You can do that using Proto 3 and using the any type to do that. This is important because in our case we want what I'm presenting here is a detector. You have to imagine the server as a job to do, as something that needs to do. This is just a small component that has to be as efficient as possible and be very efficient on the wire. And we want to minimize the complexity of the system. And we want to just be able to use a single channel as a TCP connectivity. I use 0MQ. And we serialize a protobuf across this channel. The receiver will have to deserialize according to what type it is. Okay, all of these, actually, if you use modern C++, this is not very hard. And again, the code, I have a reference to the code at the end. You can go and take a look if you're curious. I don't know the size of the thing. I think it's a few kilobytes. We can take a look in a second, but it's very small, it's very efficient, very fast, doesn't consume that much resources. And essentially, by and large, he has to do only one thing. He has to receive a message from the other server. And then, as I mentioned, based on the type, it will deserialize in a different way. And then we'll send an OK to say, OK, got your message, I'm alive, all good. And this is just one example of one of these methods. So when I receive a report, this is what happens. A quick comment on that, a so-called naked pointer, because I don't know how many of you guys are familiar with C++, but as of C++ 11, you should never do this again, ever in your life. You should never call new on a pointer. The reason why and the code that I'm writing is actually C++ 14, but the reason I need to use this is because I'm interfacing with protocol buffers. They were much older technology. I think it's C++ 98 or 2003, I'm not so sure, but they need so-called row pointer, which I immediately convert into a unique pointer, which is what essentially C++ 11 introduced. They allow me not to worry about freeing the memory, releasing, and all of that fun stuff. Once this pointer goes out of scope at the end of the method here, it will get, the memory will be allocated, the structure will be called, and all the good stuff will happen. I don't have to worry about any of that. A bit more specific on what we do for the actual protocol, for the gossip. The first thing is that we want, as I mentioned, we want to make sure the information that we got is not stale, because the server that's talking to us may have all the information that we do. And so we check on the timestamp. And again, I'm mentioning here, this is not production code. You can tell it here. I'm comparing a timestamp in another server with the timestamp that I have. That's wrong. And because there can be drift, there can be all sorts of stuff. But this was easy enough and simple enough in this case. There can be different, more sophisticated ways in which you can coordinate that, or you can check that the timestamp is the same by comparing the timestamp on the report that's sent from the other server with your own local timestamp, and do some arithmetic on that. Anyway, if this information, if the server that you just told me that is alive is not in my suspected list, and my suspected is newer than yours, then I'll add that server to my alive list. Which also means that if the server that you're telling me about was suspected, it now becomes again alive. And now I know that the server is no longer having trouble, it can receive traffic without any problem. And we do exactly the same for the list of suspected server. For a start, we check if it's us. If they're talking behind our back about us, and they're saying, well, that node is dead. Well, no, actually, no, I'm not dead at all. I am alive. And so I will tell the guy that sent me the thing, I will tell him, hey, no, I'm alive. I'm doing really well. Thank you very much. Then we'll do similar check here, but reverse, and then we'll add the suspected to our list of suspected servers. All right, as I mentioned, the full code is on GitHub. You can go take a look, copy, send me pull request. I'd love to see that. If you think there's some bugs or some stupidity, by all means, do that. I'd love to do that.
Marco, I have one question.
Absolutely, go ahead.
Yeah. How important is the time to be accurate for this to work?
Not very much, and that's why I can get away with this, which I would otherwise would have never gone past my own code review. It doesn't, because as I mentioned, this is the protocol will converge. So let's assume that the information that you send me is actually newer, but for whatever reason my clock is skewing, so I'm not accepting it. Eventually we'll get again this information with an older timestamp. So long as the skew across nodes, I am assuming that is a well-maintained cluster, that there, for example, all the servers are on the same time zone, ideally, or on UTC 2021. Folks, if you manage clusters, make sure all your servers are on UTC, and they're all are synchronized to some sort of NTP server. So the skew shouldn't be too bad. So eventually we will converge.
Sure. So, did you come up with any threshold for this queue, like seconds?
It depends. No, because it depends on the application. What is your cluster doing? You have to remember this is just like a brake light on your car. It's an element that it's a detector. Depending on what if your cluster, Daniel mentioned financial services. If I'm handling, if I'm doing what's it called, fast trading, then nanoseconds matter. If I'm if you're doing Snapchat or a messaging, a chat app, even if we're off by a few tens of milliseconds, that doesn't really matter.
Got it. Yeah.
All right. If there are more questions, let's go for the scary part, which is a bit of a demo. And this is what's gonna look like. I have a script that starts a number of nodes. You can imagine, for this thing to work, you need to, when you start up, you need to know at least one other server in the cluster, and then you learn about the others, but you need to be able to connect at least to one node. And so it's called, you will see it's a so-called a seed server. It's in the invocation. You need to know at least one server, which I'll go and try and ping, and if I get a report, then I'll know about all the other clusters. So we'll start 10 of them. And the trick that I'm doing in my demo script, I am only making each node talk to the most recent one, not all the other ones. And then we look just at the status on the first one, and we'll see how fast it does it take for the first one to know about the entire cluster. And then we simulate a failure. We'll take down a node and we'll see whether that propagates across the cluster. And then the script also starts a disconnected server. We're simulating a network partition. We're starting 3 servers, which are connected among them, but they're not connected to the main server. And then we'll try and add that functionality to the server and see whether we can simulate a partition healing. All right, let's see if this works. All right. I don't know if this is at all visible, maybe not. Can you guys see this?
Yes, we can.
Yeah.
Sort of.
Okay, excellent. All right, so this is what I'm going to do very quickly. I'm going to start 10 nodes. Each one of them is going to know about the previous one. And that's pretty much about it. And then we're going to wait a second just so that we can do that. And then after 30 seconds, I'm going to start another 3 nodes. And they only know about each other, but they don't know about the other server. I have each of these detectors exposes 2 ports. One is the TCP port, which is used for the gossip protocol. They talk to each other. And then a simple HTTP port, which I use to do this, essentially to get it's an API that returns me a JSON, and this is a simple UI that I'm running Node.js to get a state of thing. So at the moment, there's nothing up and running. Let's get going. Okay, so the first server is started at some port 8081. So let's connect to it, see what it says. Okay, it's there. He only knows about itself, as you can tell, and that's pretty much about it. The other servers are starting. Let's see if I can make this bigger. Okay, let's see. All right, so as you see, almost immediately, this is still the first one, but he knows about all of the other 10. And there's 11 of them. It's because he starts from 0. And so he knows about all of them. Now I'm starting the other 3. These 3 are not there, so they're still just 11. And if you connect to 8101, as you can see, these 3 nodes only know about them. There are 2 disconnected clusters. Okay, so what we want to do, and I knew I would forget something. I hadn't started Postman. I do apologize. I don't know if this will work. Yeah, it works. Okay. Can you guys see this?
Sort of. Can you see that, Daniel?
I can
Anyway,
see
it's
that,
not.
but
It's not
I imagine,
particularly
yeah.
exciting.
It's a bit small.
Essentially, yeah. It's not particularly exciting. I promise you that. But essentially, we are posting. We are sending to one of these 3 servers, 8103. This guy. This guy knows only about the other 2 servers in the cluster. We're telling, listen, there's another server, at least one. There's actually, we know there's another 11 that's responding on this port 777. This is the very first one we started. I know you cannot see this, but it's the first one we started. And we're essentially telling about it. So that's what we do. Okay, he says the response is there. Okay, got it, added, it's there. Let's see what happens. So you see, he has added that server. And then at some point, and immediately now knows about all the others. So it has found the rest of the clusters, even though he knew only about one. Gossiping with this one server, now he knows the existence of all the others in the class. Okay, let's see what happens if we kill one of these guys. Yeah, you look like. Okay, so I'm taking one of these guys and we're killing them. Apologies. Okay, so you can see that now it's been detected by at least one. So we can go So you can see now it's in the suspected list. There is this server, port 7784, that is now suspected. A bunch of the servers have detected it. You can kill another one. Which one? This one. And if we do that, so you can see now that we have the new one that we just killed. The other one is gone because the grace period has passed. And so now we know that that server is gone. And so it's no longer in the, you see in the active, there are only 11, there's no longer 13. And in the suspected, there's just this one. And after a while, if I refresh, let's do that. Takes a bit, probably 30 seconds or something. And it's gone. So it's no longer in the classes. So now we only have the 11 servers.
And Marco, just to check, so what we're saying here is basically if no other node can connect to that suspected server, and it'll effectively drop off the radar of the entire cluster, right? It'll just vanish for all.
Correct.
Yeah.
Not only that, but even a server, any other server, even if you didn't try to connect the server, now he knows that it's suspected. Yeah. And so you may use this information. So let's say that, for example, you brought up Cassandra. Cassandra is a great example. Cassandra uses replication across multiple nodes. You can set a quorum and say quorum of 3. So I need, for accepting a write, I need to be able to replicate at least 2 servers. Now, I can have a configuration such that actually, because it uses consistent hash, you have several buckets. You can have 4 or 5 servers that I can replicate my data to, but I only need to replicate to 3. Well, if one of those 5 is in the suspected, I will send to the others. So I don't have to wait. I don't want to run the risk. And so I can put them in kind of on a back burner or not communicate with them at all. So that I don't risk essentially trying to talk to a server that potentially is not responding to me, or is even very slow to respond, which is even worse. Because as you know, if the server is down, the HTTP protocol will immediately return you, the network layer will immediately return you refused connection. The real problem is that server accepts the connection and then it sits on it. So now you're wasting a lot of time waiting for that guy to respond to you. Probably may never will. And that's actually what I mentioned earlier. That's probably the worst possible situation, is a very slow responding server. Server that crashes is fine. You just restart it and everything sort of works.
Yeah, that's very interesting. Mm-hmm.
All right. I'm glad the thing worked. It wasn't particularly exciting. I do apologize. And there's no fireworks. But that's life in the back end. You get. I mean, we're lucky that we're not looking at logs.
This is it.
Life.
By the way,
yeah. No,
Daniel, you said you guys were hiring. Well, if you guys have a UX job, don't give it to me, because as you can tell, I'm horrible.
Right. Well, for the Cassandra demos back in the day, what we often would do is have them set up on networks of little Raspberry Pis, and then
yep.
we would literally take a sledgehammer to one and watch, the throughput drop by the prescribed amount, but otherwise, you still have replicas, so no data is lost.
Yes.
And we would actually get people out of the audience to take the sledgehammer to these little computers. It was, one way to make the back end interesting at a conference. Anyway.
That's cruel but effective. By the way, I used Cassandra in a project I did at Apple. It was a pretty large scale data center replication, and my QA guys were going nuts because they couldn't verify failures. Essentially, the thing would fail, but they couldn't. nothing would appear. It would still work. Everything was fine, and so they couldn't essentially confirm the failure scenario because nothing happened. It was just work. It was fun. All right, guys, this is pretty much the end. As I said, there's the code. It's on Apache 2 license. It's available on GitHub. You can go there, throw tomatoes at me if you don't like it, or send me pull request. There's a blog. I have a few things that I publish there irregularly. My LinkedIn profile, and also I wanted to promote a bit a bunch of stuff that are behind the scenes in this gossip detector. It comes from a distributed system utilities that I'm writing in C++. It's called dislib. It has an implementation also of consistent hashing that Cassandra uses, Merkle tree that's using blockchain, and also just finished implementing a distributed key value server, because then the world needs another key value store. And so I thought I would definitely do that. Yeah. Just joking. It's just fun. Anyway, that's it.
We have a question. We do have a question.
Okay.
Also, unless you would like to ask it yourself, I'm happy to read it. Yeah, I'll do it then. So the question is this applicable for only large scale clusters? Is there any use case for small and medium environments to make use of it?
Absolutely. You can, it really shines in large classes because the alternatives don't shine. They cause trouble. But of course, this is perfectly valid. It works great. As you see, it takes fraction of a second. If you have a cluster of 10, 15, 20 nodes, and it should take, depending on how you set up your timeouts and your grace periods, below 2 seconds, you detect that the server is misbehaving. And then you can take it out of rotation or whatever. So it works just fine. And as I said, given that the implementation, it's very efficient and very performant, is no worse than just having a heartbeat. Because the alternative is you have a small cluster, each node has a /health endpoint. You keep hitting it until it doesn't respond. This one actually is more efficient also on the network. On the network, it's much lighter because you don't have to hit all the servers all the time.
You did sort of start answering what was going to be my question. I believe I know the answer. It's more of a prompt, but if you would talk about this concept versus an agent and mothership kind of approach, right? So I mentioned I also worked for AppDynamics, but this is the same for Datadog or Dynatrace or any of them out there. Why is this useful? Why is this better in some ways? Are there any weaknesses versus more of a centralized approach? What's your take on that?
Yeah, again, this is fairly similar to blockchain, if you will, right? It's a completely distributed system. All the nodes know about every other node, and if any node goes down, it doesn't really matter because all the other nodes have all the information that they need. The challenge that you have with that kind of agent mothership pattern, as you described, which is similar to what you have in, for example, in Kubernetes with your controller node, is that to implement HA, you need to replicate that node. You need to replicate state across the node. And then you have an interval of time. For example, if you use election, something like Paxos or whatever, to elect a new leader, you have an interval of time during which you are leaderless. And so everything has to halt until the new leader comes up. It's very much like, in political life these days, there's a period of time until the new leader comes on, then everything grinds to a halt. I saw there's another question coming around. So,
yeah, we have another question from the audience from Naveen. What protocol does this use to check health of the nodes? Something like consensus?
No, it doesn't. That's exactly the point. It doesn't use consensus. So the protocol is this gossip protocol. The gossip protocol is the protocol. It essentially uses, to be more specific, uses 0MQ. It's a TCP layer, and it sends data across the nodes. And so each node, and it doesn't just do a ping, as I mentioned earlier. Each node sends the report, and they use the report send to check on the health of the receiving node.
One question.
Sure.
Is this suitable for workloads which are sensitive to battery life, which don't have any constant?
Oh, great question. Great question. Oh, never thought about that. So it is suitable to the extent that, as I mentioned, you can tweak it, right? You can make it. You have at least three. I mean, I would have to look at the code to remind myself, but it's certainly three knobs. One is the interval between pings between the nodes. You can, if you are concerned about battery life, you can reduce that. Now, of course, your information is less fresh, if you will, right? The less frequent the pings, the longer the interval between updates. So that's one trade-off that you can play. The second trade-off that you can play is on the timeout. After you send a ping, you wait for the node to respond to you. If it's a very long timeout, you keep that connection open for a long period of time. So and so that may have detrimental effect on your ability to detect failures. And then the third probably has less of an impact. The third knob is as I mentioned, the grace period, the amount of time that you keep a node in the suspected state before evicting it and assuming that has failed. I doubt that that has any impact on the things like battery life.
In terms of the network, in terms of traffic, right? The pipe is going to be very small in case of things like edge use cases. How busy do you think is going to be?
So actually, it's a great question. One thing I forgot to mention. Thank you for the question, because there was something I forgot to mention is that as you saw, we send a report with a link. Here, I send a report. Now, this report contains which actually I think is there, a repeat, so a list of the alive and suspected. Now, that's something that I can tweak, and which actually I do tweak in my code. I use a quadratic cost. Just thinking, I have some information about some server, and some information is fresher than other information, and it's kind of old news. I mean, it's very much like gossip. You like gossiping about something you just heard from your buddy, not something that you guys spoke about a week ago. That's not so cool, right? And so that essentially takes the same approach. I take a cost, you can apply a cost function, and so I truncate the length of the report when the cost of sending additional information exceed a certain threshold. In the example you just made, if I want to minimize my network load and I want to send very short report, I can lower the threshold. So only very recent information that has reached me gets propagated across the servers. Now, the downside is that servers that join the network late will not know the full state of the cluster. If you saw when I was reconnected, that those 3 servers in that island to the main cluster, they immediately knew about all the others. But if it was a very large cluster, information was fairly stale at the end, they might not have learned about all of them immediately. It would have taken some time to learn about that.
Okay, thanks. Yeah.
Fantastic. Any other questions from the audience? Okay. Well, I dare say we might wrap up exactly on time then, which is quite the feat in itself.
Amazing.
Yeah, not bad at all. Well, thank you very much, Doctor, but Marco.
That's a joke, but
yeah, there's a lot of secret PhDs at Styra as well, and I find out, oh, you have a PhD in computer science, and I find it out after knowing him for a year. So, but yes, thank you very much, Josh. Do you want to close us out at all with some final words?
Yeah, I'll close it out. Marco, thank you so much. And your demo did not crash, so congratulations.
Yeah, disappointing that.
I know that was kind of nerve-wracking. So really, really want to thank you for coming with us today, and really appreciate that. And I want to let everybody know that our next event is going to be on Tuesday, March 2nd, and we'll send, I think it's already been announced actually, but we have Rajesh Iyer, who's the platform engineering manager at American Express. And the title of that event is Solving the Interoperability Puzzle, an Event-Driven and Cloud-Native Systems. So we're really excited to have him, and that's going to be the next one. And then we also have a couple other events lined up already that we'll be announcing later this week. So yeah, that's it. We will share this. We got the recording here. We'll send that out to you tomorrow. And I think that's it. So thank you, everybody. If you haven't joined our meetup is Cloud Native at Scale on the meetup platform there. We're based in San Francisco, and that's it. So thank you, Daniel. Thank you for hosting this event. Really appreciate it. And again, Marco, thank you. And we'll talk to you guys soon.
Thank you so much for having me. I really appreciate the opportunity.
Take care now.
Thank you so much.
Bye, everybody.
Bye.
See here.